This is from 2018. Um, no calculator, which now most of all of the exam is no calculator now. So, you could use a scientific or your phone, but you don't need it. So, they're going to give you, I'm assuming they give you something like this, where you have a graph, and you could see like the first from -5 to 3, right? You could see that it's all piecewise, meaning linear, right? Piecewise, and then after 3 you have that parabola 2x minus 4 squared. So we need to use those to figure out these 4 parts of this problem. So for part A, they're saying we know f of 1 is 3, and we want to find f of -5. Okay, so in order to do that, right, you have to think of what is given. So they give you this continuous function g, but that's the derivative of f. Okay, so because that's the derivative of f, if we go backwards, we take the antiderivative, we could get our original function f. So we want to take the integral of g. Okay, so what we're going to do is, if you look at our integral, and let's use the values that we have. We have -5 and we have 1, and then we have our function g of x dx, right? Well, if you're doing that, okay, we know that that's going to, since g is the derivative of f, we know that we're going to get f of 1 minus the f of -5. Well, we already know f of 1. We don't know f of -5. So I'm going to rearrange some things, and I'm just going to bring it over. So I'm going to do f of -5 is going to equal f of 1 minus this -5 to 1 of g of x dx. All right, so that helps us in a little bit so far, but not anything great yet. But we do know f of 1 given to us. So we have f of 1. Now, our integral, right? So if we're going -5 to 1 of this integral, really all we are looking for is what is the area under the curve. Okay, if we know the area under the curve, then we could get what f of -5 is. So f of 1 was 3 minus, and now let's go back up to our graph. So -5, right, to 1. That's what we want to find. So we could do a couple things here. Let's split it up. We have this rectangle. All right, so this rectangle is 3 by 3. So we get a 9, but remember it's below the x-axis, so that's negative. We also have this little triangle that's 1 by 3, so that's -1/3. Okay, and then we have this other triangle here, which is 1 by 2. Ooh, I messed that up. That's not -1/3, that's -1/3 divided by 2, or -1/6. Okay, and then here, right, we have 1 by, what am I doing? No, this is 3 over 2. What am I doing? So it's -3 over 2. Sorry about that, guys. And this is 1 by 2, so that's 2 divided by 2, you get 1, and that's positive. All right, so here now we'll have this -9 minus 3/2, and then a +1. Okay, when we do all that, we get 3 minus a -18. Yeah, -19/2. So we're going to get 6/25 halves as our answer. Okay, so that's the first part. Common question. I am assuming you're going to get one like that, it's going to look that way. To evaluate part B, right, we are going the integral from 1 to 6 of g of x dx. So again, we're looking for the area under the curve, but let's go back up top. So now we're going from 1, right, we're going from 1 to 6. If you notice, there's two different functions here. This one's nice. This one's 1 to 3. This is 2 by 2. We get an area of 4 there. That's a good one. Okay, we get an area of 4. All right, and now we have to do some integration, you know, because we have this function. We can't get the exact area unless we use our rules. Okay, so what I'm going to do is I'm going to break this up from 1 to 3. Everybody see that? You know, 1 to 3. G of x dx plus 3 to 6 g of x dx. All right, so we already know, right, if we already know, like going back up top, that 1 to 3, that was an easy one because it's just 2 by 2, so we know our area there is 4. Plus, now we have this 3 to 6, and we have our function 2x minus 4 squared dx, and that I just got from up here. Okay, so just going through taking antiderivatives, I mean, if you need to use a u sub, go right ahead. I don't really think we do. We could just use our power rule here, right, because the derivative of the inside is just 1. So there's our power rule, and now we're evaluating from 3 to 6. Okay, so when you do that, keep the 4. We get plus, so you're plugging in 6. That's going to give me 6 minus 4, 2 cubed, right? So this is 16 thirds minus, if we plug in 3, you'll get a negative 1, so that's a negative 2 thirds. And that works out actually very nice because 4, this is going to give me 18 thirds, which is 6, and so I get an area of 10. Okay, so those are the first two parts of this. Okay, the next part we have 4, negative 5 to 6, so the whole graph. And what I'll do is let's erase what I have here. We don't need this. I mean, we may, but right now we don't. Okay, so on the open interval, if any, is the graph of f. So again, right, oops, again, thinking about what the function f is, right? So we have the derivative of f, which is here, okay? And they're asking both increasing and concave up. All right, so what I want to talk about in this one is increasing. This is our derivative. This is f prime. So increasing, we're just looking at to be positive or above x-axis. So right now, I'm only concerned about 0 to 6, basically. 0 to 6, it's all above the x-axis. And then concave up, since this is the derivative, I want to see where is the function increasing. So increasing, right, can be, you know, you have an increasing from 0 to 1, and then you have, again, 4 to 6. So that is what I'm looking for. And when you give your reasons, those are the reasons why. So, you know, however you want to write it, I would say like 0 to 1, right? And then again from 4 to 6 is where f is both increasing and concave up, since g is equal to g is equal to f prime, and it's greater than 0, and how else do you want to say it? And the same idea, since g is equal to f prime, and the graph is increasing. Okay. All right. Last one we have. Find the x-coordinate of each point of inflection of the graph of f. So let's look at this again. Let's erase some things, right? So we're looking for points of inflection now. Points of inflection, it has to change from concave up to concave down, or down to up, right? Down to concave up. So the other thing is, knowing that this is f prime, really we are talking about increasing and decreasing. If it is increasing, we know it's concave up. If it is decreasing, we know it is concave down. Okay, so when I'm looking at this, right, points of inflection are going to be where it changes from increasing to decreasing. So it doesn't start to change. This is like, if you go from -5 to 2, all right, it's flat, nothing. It increases -2 to 1, but it doesn't really change. -1 to 0, flat again. 0 to 1, increasing, and then it stays flat, and then it starts to decrease again. So in this problem, the only time that it changes from either increasing to decreasing or decreasing to increasing would be at this point 4. And that's really all you have to write there. All right, so at x equals 4, function f has a point of inflection since f prime, which is equal to g, right, changes from decreasing to increasing. Okay, hopefully that is a bit helpful.